Hi all, in this video I will demonstrate the new Cyclone separator generator module. Now if you open the window, you will see on the left side the settings, and in the viewer you will see your final geometry. So if I hit the preview button, you will see that one Cyclone separator is created. It has several sections. The inlet, in orange in this case, we have the main body, the cylindrical section, the conical section, and the dust outlet consists of a dip leg and a bin. So you can enable or disable the dip leg or the dust bin. You can collapse these, and you can also add a void, so the vortex finder will carve out a section and create the wall. You can play around with the values, like the outer extension will extend the vortex finder, and also I have a full list of preset values. Like if you go to Stairman High Efficiency Cyclone and hit on apply preset, you will get this one. It is all based on the Cyclone diameter, so all the values you see here are based on ratio to the Cyclone diameter. So if you change to high flow rate, you will get a different geometry. So you can then export this to the cut environment. Like let me choose this one, preset, and if I export this, you will see it over here, and you can tweak this geometry for the simulation. Don't forget to merge these. The reason why I did not implement the fuse operation is because you are able to change the inlet position in the cut environment or duplicate it. Like if I would like create a pattern, hit this as target and then hit this angle as rotation, and then create here like circular, and the spacing is like 180 degrees, and apply, and you will get like a dual inlet structure. You can hit the key E, it will accept, and if you want to fuse these, you can hit these three, hit apply, hit source button, unify domain, hit apply, and you will get your Cyclone separator. You can of course include dip leg, dustbin. You can play around with the values. You can do whatever you want. You can also create an apex core. It will be created at the bottom, and you can move it around in the cut environment, like when I export this. And let me change the transparency, and we will select the apex cone, and you want to move this around. Like this, for example, hit key E, and then we will apply a cut operation, hit key E, change the transparency of this again, and you will see that you will have an apex cone right here, and you can proceed with the meshing process. So another cool feature of this is I did also write the Muschelknots method to simulate the performance of the Cyclone. Like, it will grab all the dimensions of the Cyclone from the left side you already created for the actual geometry, and then you can input your values. You can input your solid loading and your particle size distribution. Let me put a value. Actually, let us do that more professional, like 1, 2, 3, or like 6, and our cumulative fraction would be like 3, then what else, like 6, and then 1, and then you can hit this run simulation and it will calculate your grid efficiency curve. Actually, we need to change a couple of values. The inlet velocity in this case is like this. Normally it is much higher, like 10 or so, and then you would have something like this. You can add more particle sizes classes, and you will get then your great efficiency curve. And if you want to learn about the implementation, where it comes from, you can hit this information button, and it is from the textbook of Hoffman and Steen, gas cyclones and swirl tubes. And in a specific chapter, it is chapter 6. It is called the Muschelknots method. So in this book there are also validation cases, and these are the points over here in different shapes. You have here your validation cases, the cyclone geometry you have here, and the particle size distribution over here, and the operating conditions. And I did calculate the efficiencies, and I did plot these with the experimental values. So if you want to check, and you can also move to other slides if there are more data. And overall I have 6 cases. The first 3 are from the textbook, and the last 3 are from papers, and I did insert these also. So these are also included. If you want to know about the original source, it is over here. Then I have these and this one, so it shows actually how good or bad the theoretical method is. And I think if you want to do a CFD simulation before you conduct any CFD simulation, it might be good to work with a theoretical model which is rather verified or validated with actual experimental data, and then you can then move over to a CFD simulation and then check how good the prediction of the theoretical model is compared to the CFD simulation, and compare it also to the experimental values. So thanks for watching, and see you in the next video.